Okay, more things on why photons are silly. We're going to take you. Yay! Here's my little stick figure. And I'm going to give you two balls. And you're going to move these balls around. But randomly, because we're going to use standard quantum theory, which is they never travel in a straight line, but they're here, then they're here, then they're here, then they're here. And I'm going to take balls. I'm going to throw them at you. And you're going to move your ball so that this ball bounces off at the same angle every time. What would we call this? We'd call it reflection. I can see myself here. So in this bell, I can see myself. So I know that the light bounces off at the same angle every time. So we're going to simulate that by having you move the balls around, and I'm going to throw balls, and you're going to bounce them off at the same angle every time. By the way, you're blindfolded. You don't know when I'm going to throw my ball. How many are you going to get? I'm going to go with 0. They're not going to bounce off at the same angle every time. So the idea of round hitting round just doesn't really work. So how do we solve this? And it's a pretty easy thing to solve. First, we get rid of our photons because they're just silly. Light's a wave. That's it. That's what it is. Okay, next we have our material. And our material in metal is going to have an underlying structure with bonds, and I know I drew it more like carbon, but you're going to have an underlying structure. And then we're going to have a bunch of extra electrons in metal, okay? And they want to get as close to the center, but these bonds that are around each one of these are negatively charged. So the extra electrons out here want to get in, but they're blocked by this. But they also don't like each other. So they want to get away from each other as much as possible. How do you do that? Well, it's going to kind of look like an oil drop on top of water. The electrons are going to form a thin layer. Because remember, they're not bound by a shape. They can change their shape. In this case, they're going to make the thinnest layer possible. They'll even do a little bit of indenting where they can get closer, further away. But generally, it's going to be a flat surface on top of metal. Okay, now, when the wave comes in at an angle, it bounces off or causes it to shake and is reproduced. Either one, it doesn't matter. I like to think of it as it bounces off at the same angle every time. So now for the trick question. On the surface of this shiny material, how many electrons? The trick question is 1, just 1. It's really big. But they're not individuals. They can take on shapes and they can merge and split. The thing that we know as an electron, the standard electron, is like a droplet of water. If I take a glass of water and I throw it onto the table, I'll end up with a puddle, but I'll also end up with a bunch of little droplets around, and they'll be about the same size. Water has a size it likes. It's about the size of a rain droplet. Electrons are the same. They have a size that they like. And that's the size that when we shoot them or they're emitted by themselves, traveling through gravity, that's the size they take on. But it's not always the size. In a bond, like one of these bonds, which may loop around both pieces of metal atoms, it's one charge. It may have the weight of 8 of these or 2 of these. It'll have the weight of a number of individuals, but it's not individuals. You have to stop thinking of them as individuals. If you stop thinking of them that way and think as a group of 8, and remember from before, we have a wave riding on the surface, and this wave determines the shape of the charge. And the charge would like to collapse in again, but the wave prevents it. These guys have a wave, but it's not a quantum wave. It's just a temperature wave. Okay, what keeps them in the shape was they're trying to get away from each other as far as they can, but at the same time, trying to get as close as they can to the center with these fixed waves blocking their way. So again, it's like the drop of oil. When you drop oil onto a water bucket, it runs out thin. It doesn't want to get to the water. It wants to get to the ground. The water is in the way. The water repels the oil. They don't mix. So it wants to get as close to the ground as possible, but not mix with the water. That's a thin layer, and that's the same thing that happens in metal, which is what gives us reflectivity.